Today we will be presenting to you the piezobrush PZ3. This is a case that some of you might know from our previous product or still current product, piezobrush PZ2. But during the unboxing, you will see a few changes. So the device itself has changed a bit in shape. I'll put it down for you here. There we go. And you can see there is these white yolks. We'll be getting to them soon. Just hook it up. Again, plug-in power supply, as you know, just needs a standard wall socket. And the other side, of course, will be hooked up to here at the back of the device. And you will see the screen. This is a new feature, the display lighting up. So now we have a message here saying there's no module inserted. So module, we'll be coming back to these white fellas. I'll just select this one. This one we call the standard module, and this is for non-conductive materials. Just place it upside like this, and we'll insert it, fill it. Okay. Now, if you can see that, it detected the standard module. And basically now we're ready to go. Of course, main question, what is this tool used for? For that, I would like to get back to the standard kind of the basics really of surface energy. So surface energy really fundamentally means we have a surface and we want to know how active is it to bonding processes. And we can probe that by putting down droplets. So basically just water droplets, that will do. And if you see the droplets kind of beading together like that, like you see in the left-hand picture, that means we have low surface energy. A high contact angle is what you look for. And this means it's insufficient wetting, weak bonding. After the treatment with the atmospheric plasma, you will see that the surface has changed, since if you put down a droplet again, the droplet will spread out on the surface, the contact angle will decrease, which means an increase in surface energy, and therefore increased wetting, and typically stronger bonding. So just to demonstrate that to you, this is a material that most of you will know. This is the ABS material. You can see we have a protective layer, so this is completely clean. Let's pull that off. And I have prepared corporate design ink for you. So here we go. You can see if I put down the droplet. There we go. They're round. They're kind of beading together. You can see that here against the white background. Now, application is really easy. We just press this button. You can see the generation of the plasma. The display shows you all fields are green. We'll be hearing more of these. And there's a stopwatch that's counting up the seconds. So we'll be basically just moving over the surface fairly closely to the surface. That's already it. And now if I put down another drop, you will see that the behavior has changed. So you can see here that we have a spreading of these droplets. And we can also probe the surface by the means of testings. So I will choose a number. I'll choose number 60. Just these are fresh, so I'll just open them here. And what you will see is these are typically blue. If I apply this to the surface, there's only testing in the area where I have treated. So the testings are great for just looking at the homogeneity of the treatment. So 60, what does that mean? I'll give you a bit of an overview just for you to kind of get an idea or feel for these numbers. So the surface energy is, of course, measured in millinewton per meter. you see the material that I was just treating, ABS. In an untreated state, it has something around 45 millinewton per meter. But you can also see that the surface energy splits up into two parts. One is the dispersed part and one is the polar part. The dispersed part is typically probed with a solvent, like an unpolar liquid, for example, diiodomethane, and the polar part is probed with water. After the treatment, you can see that we have increased, we're over 60, and that's the reason that we have wettability of the ink that has a nominal surface energy of 60. And to kind of put that in perspective, if you look at the lowest bar we have there is PTFE. Of course, you know that material, that's really hard to wet, and it has a very low surface energy of 15. The highest surface energy that we typically probe is 72. That's the wettability of water. And typically to get a good bonding, you would have to go over 50. That's kind of a rule of thumb. Okay, speaking of PTFE, we have that material here as well. I'll just pop it out over here. So PTFE, as you can see, again, let me put down a drop. Yeah, like Lotus effect, huh? So these really bead up. Now if I use the piezo brush again, same thing, and just treat one side of it. You can see that the contact angle has decreased. We'll move on from how does wettability have something to do with bondability. We have a lovely little image that we made where we explain a bit how these two go together. So I already explained with the droplets, but now we look at kind of the molecular structure. So what really happens with the atoms. Typically for bonding, the uppermost atomic layers are really significant. So about 5 monolayers of the surface. If you have like a PTFE, these layers are more or less inert. So there's nothing, no bonding sites really to engage in bonding with the liquid, say the ink, for example. And what we do with the plasma treatment is we generate end groups, like anchor groups. And these anchor groups, again, are typically polar because we work at atmospheric conditions. So we work a lot with oxygen species. And these groups can correspond to polar groups in the liquid and therefore form a chemical bond. So now the question is, what about metals, for example? Metals, as some of you might know, are not really the ones that we functionalize. What happens with metals? So this is a stainless steel sample. If you look up the surface energy of stainless steel or metals in general, they have very high surface energies. But now if I look at it with my droplet tests, I mean, they don't lie. We'll have this, again, this beading of the drops. Like it's nearly as bad as the PTFE sample. So of course, what will we do? Treat it with a piezo brush. I will show you the proper way to treat a metal, and that is with the near field module. This is what we call the near field module. Looks similar, has a different color of the label, and it says here it is for conductive material. Same thing. And you can see here it detects near field. What happens if I put down the drop now? On the side. Ooh. There we go. Wettability of the surface has increased. And why is that? So now we didn't generate end groups, did we? No, what we really did is, we'll show you another figure to kind of explain that. The metal has bonding sites, but they're not available. All processed materials have some kind of contaminants on them, and these contaminants inhibit these bonding sites. So even though you might be able to bond on the material, as I said, only the upper layers engage in bonding. Now these are kind of covered with contaminants, as you can see in the picture. So again, we have low surface energy because we're actually not probing the surface. We're probing the surface, like the layer of contaminants. And if this is a very thin layer, so a couple of monolayers, we can reduce these contaminants by using, as you saw, the piezo brush. And then we'll make these bonding sites available again, and therefore we have better wettability and typically better bondability. So we learned about wettability as a crucial indicator for your adhesive process. Also, contact angle measurements, testings to determine the surface energy. Then we learned about contaminants. Yeah, they're nasty, but that we can decrease these contaminants and increase the quality of adhesive processes by using the cold plasma of the piezo brush for fine cleaning. What we really do here is we oxidize these contaminants. And with the plastics, even if they're clean, we have low surface energy, and we can increase that surface energy by functionalizing them. Okay, so all in all, the cold plasma of the piezo brush increases the wettability and typically optimizes your adhesive processes such as gluing, printing, coating, varnishing.